Welcome to Copernicus AI, Frontiers of Science.
Today, we're diving into the electrifying world of quantum computing, a field constantly pushing the boundaries of what we thought possible.
We're specifically zeroing in on recent breakthroughs that aren't just incremental improvements, but genuine delta shifts in how we approach building fault-tolerant quantum computers.
These are developments poised to fundamentally reshape computing and our understanding of complex systems.
That's all you, Sarah.
It's an incredibly exciting time.
For years, the noisy intermediate-scale quantum, or NISQ era, has been characterized by machines with limited qubits and significant error rates.
The true revolution, the paradigm shift we're seeing now, is the focused effort on moving beyond NISQ by tackling quantum error correction head-on.
Recent experimental demonstrations, particularly involving surface codes and other robust error correction techniques, are truly game-changing.
Maya, can you elaborate on what makes these error correction developments so revolutionary?
I thought quantum computers were inherently fragile.
How can you correct errors in something so delicate?
That's an excellent question, Tom.
You're right. Qubits are extremely fragile.
They lose their quantum coherence very quickly due to environmental noise.
Quantum error correction isn't about perfectly shielding individual qubits, but rather encoding information redundantly across multiple physical qubits to protect a single logical qubit.
If one physical qubit in the logical encoding flips an error, the quantum error correction code can detect and often correct that error without actually measuring the logical qubit and destroying its superposition.
Think of it like spreading a message across many messengers. If one stumbles, the message still gets through.
This is the bedrock for truly fault-tolerant quantum computing.
So, this isn't just about making individual qubits better, but about a completely new architectural approach to manage their inherent instability.
What specific recent research exemplifies this delta in error correction methodology?
A standout example comes from recent work demonstrating a distance-3 surface code, and others pushing the boundaries of error suppression.
For instance, a paper by Marquez et al.
In Nature Communications in 2023, Marquez, G.
Realizing a distance-3 surface code on a 17-qubit superconducting quantum processor.
Nature Communications
showed significant progress in implementing a distance-3 surface code on a superconducting platform.
This is critical because the distance of the code relates directly to its error-correcting capability.
A distance-3 code can detect and correct a single error, marking a crucial step towards more complex, higher-distance codes needed for practical fault tolerance.
That sounds incredibly complex.
What does distance-3 surface code even mean in practical terms?
And how does one actually implement this on hardware?
Good point, Tom.
In simple terms, a distance-3 surface code means that to protect one logical qubit, you're using 9 physical qubits arranged in a grid-like fashion, with additional qubits for measurement and syndrome extraction.
The surface refers to this 2D arrangement.
The implementation involves carefully choreographed sequences of 2-qubit quantum gates and single-qubit measurements.
These measurements don't reveal the logical state directly, but rather reveal syndromes, patterns of errors.
From these syndromes, algorithms can infer where errors occurred and apply corrective operations, all while preserving the delicate quantum state of the logical qubit.
The challenge is that these operations themselves can introduce errors, so the physical error rates must be below a certain threshold, often cited around 1%, for the QEC to be net beneficial.
The Marquez et al.
Paper is significant because it achieved coherent error-corrected operations for a logical qubit, showing the viability of this approach.
That's a profound shift.
We're moving from merely observing quantum phenomena to actively engineering systems that can sustain and correct these phenomena.
What are the broader implications of successfully demonstrating these error-correcting codes, both for computing and potentially beyond?
The implications are vast.
For computing, it unlocks the path to genuinely powerful quantum computers that can maintain coherence for long enough to tackle problems intractable for classical machines.
This isn't just about faster computation. It's about solving problems that are currently impossible due to the exponential growth of complexity.
Think about molecular simulation for drug discovery, advanced material science, optimizing supply chains on a global scale, or even breaking currently secure encryption methods.
Beyond computing, these advancements in controlling quantum states at scale could have profound implications for fundamental physics, allowing us to build quantum sensors of unprecedented sensitivity, or even explore the nature of spacetime at microscopic levels.
So, are we talking about a new era where we can finally build machines capable of quantum supremacy on a consistent, reliable basis, or even quantum advantage in practical problems?
Precisely, Tom.
While quantum supremacy focused on demonstrating a task impossible for classical computers, QEC paves the way for quantum advantage, solving practical problems faster or more efficiently.
Recent work, such as that, by Kim et al.
In Nature in 2023, Kim, H.
High-fidelity quantum operations on individual neutral atoms in a 2D array
demonstrates incredible fidelity in neutral atom platforms, which are another promising avenue for scaling up quantum systems.
These high-fidelity operations are crucial for QEC to work effectively.
We're moving towards an era where the dream of a fault-tolerant quantum computer is shifting from theoretical possibility to engineering challenge, albeit a monumental one.
It sounds like we're not just building faster calculators, but fundamentally new types of machines that interact with reality in a different way.
How do these breakthroughs connect with other fields?
Is this purely about computer science, or are there interdisciplinary ripples?
Absolutely. There are massive interdisciplinary ripples.
The development of robust quantum computers impacts fields from chemistry and material science through advanced simulations to finance, AI, and even fundamental physics.
The engineering challenges are pushing boundaries in cryogenics, microwave engineering, and optics.
Furthermore, the theoretical frameworks for quantum error correction draw heavily from classical coding theory and topology, demonstrating a beautiful convergence of mathematical concepts.
The very act of understanding and mitigating quantum errors pushes our understanding of information theory and the limits of computation itself.
So, if these error correction methods work, what's the next big hurdle?
Is it just a matter of scaling up? Or are there more fundamental scientific questions still to be answered?
Scaling up is definitely a monumental engineering challenge, coordinating millions of qubits, maintaining their coherence, and routing information.
However, there are also fundamental scientific questions remaining.
For instance, developing even more efficient QEC codes, understanding how different qubit architectures perform under various error correction schemes, and bridging the gap between theoretical error thresholds and practical implementation.
There is also the fascinating intersection with quantum gravity and theoretical physics, where quantum computers could potentially simulate exotic phenomena or shed light on the nature of information in black holes.
Another significant area is developing quantum algorithms that can fully leverage these fault-tolerant machines once they arrive.
We need the software to catch up with the hardware potential.
Work by O'Gorman et al.
In Nature, O'Gorman J.
Realizing quantum advantage with a 61-qubit processor.
On achieving quantum advantage with specific algorithms highlights this need for both hardware and software co-development.
This discussion really underscores how these quantum computing breakthroughs represent not just technological advancement, but a profound delta in scientific thinking.
We're moving from simply observing the quantum world to actively shaping and controlling it to solve problems previously deemed impossible.
We're witnessing the groundwork being laid for a future where quantum machines move from research labs to powerful tools that could revolutionize everything from medicine to climate modeling.
It's a testament to human ingenuity and the relentless pursuit of understanding.
And it sounds like there are still so many fascinating unknowns and challenges, making it an incredibly dynamic field for researchers, investors, and even curious minds like mine.
Absolutely, Tom.
This journey into fault-tolerant quantum computing is a testament to humanity's drive to push the boundaries of knowledge.
The implications of these recent error correction advancements are truly paradigm-shifting, paving the way for a future where quantum machines tackle challenges previously beyond our reach.
We'll continue to track these frontiers on Copernicus AI.
Thank you, Maya and Tom, for this illuminating discussion.